So, welcome to the next in our PML School series. This will be the PK number 3 from Gabrielsson and Weiner. This is a one-compartment PK model, and we will be fitting and comparing first and zero-order input models. I would like to mention that through the course of this presentation, if you have any questions, there is a Q&A panel on the right-hand side where you can type your question. And we will have a Q&A session at the end to answer questions from the list. If we don't get to all of them, we will present answers to all of the questions on the forum. So thank you again for joining today. The background for this exercise, PK3, one subject received a 20 milligram oral dose of a highly polar drug, and concentration samples were collected from the plasma. From previous IV bolus studies, the drug is known to have a one-compartment elimination. Okay, so an exploratory plot of the PK profile. This is on a semi-log scale. So the plasma concentrations versus time, we see here we have the one-compartment elimination, but the absorption phase in this case is a bit tricky. So it might not be straightforward to fit a classical library model to such a profile. So our objective here with PK3 is to apply a one-compartment model in terms of the clearance and volume of distribution, noting that generally absorption is thought of as a first-order process, although in some cases it's better described by a zero-order input, which resembles a constant rate infusion. So our objective will be to fit and discriminate between first and zero-order input models. And our parameter estimates, we'll find estimates for volume of distribution and clearance. This will be common parameters between both models. For the first-order model, we will use an absorption rate constant, Ka, first-order absorption from the GI tract, as well as a T-lag, which is a lag time to reach the absorption site. For the zero-order model, instead of using these parameters, we will use a input time, a duration of the zero-order input, referred to as T-abs. Okay, so here we have an example. If you've attended previous sessions, we've commented on the fact that the PML text gets written for you as you make model selections. So when you're in the default mode, which is what we call the built-in model, this is where you're using menu selections to set up the structural model. So we use PK model with clearance parameterization, extravascular absorption with T-lag checked, and a one-compartment elimination. And here we have the differential equations that are listed here, as well as T-lag incorporated into the dose point statement, concentration term, and then the error model. Okay. If one switches the input mode to graphical, it is possible to customize your absorptions in the graphical mode as well. And so with the first order model with T-lag, what we can do is implement a T-lag to the dose point statement. So this is the graphical model for a first order absorption. We have the absorption compartment, absorption rate constant. Here we have the central compartment, which has a volume and an amount. We are taking concentration measurements from the central compartment, and the drug is eliminated by clearance, a clearance flow. And if we want to set a fixed value for T-lag, we check this box and put in a value, for example, 0.5. If instead we want to estimate T-lag as a parameter, we add it as a parameter to the text model. Okay. For the zero-order model in text mode, this is a one-compartment model. We have the central compartment with elimination. And instead of adding an absorption compartment, as is the case with the first-order model, we're actually delivering input directly to the central compartment, and then we can edit the central compartment to say that there is a zero-order input with a value of 4. And again, when you're editing in graphical mode, this is entering the zero order duration as a constant. If we want to estimate it as a parameter, we need to do that in the text mode, as we will see in the next slide. Okay, so here's the example of the text code for the zero order model. We have the differential equation to describe the PK. So the amount in the central compartment changes over time by minus clearance times the current concentration. The zero order input to the central compartment, we use a dose point to describe a dosing event. A1 is the central amount in the central compartment, and then the duration of the zero order input is a parameter in this case declared as T-abs. Okay, the concentration of the central compartment equals the amount divided by the volume. This is the error model. This is a simple additive error model. And the structural parameters that were from the built-in model include the volume and the clearance. And we also have added the T-abs, the zero order input duration, as a fitted parameter here. Okay. So with these models, it is good to start with initial estimates for the parameters in the model. And so how would these be obtained? For clearance and volume, these can be obtained from non-compartmental analysis. The clearance, we have 45 liters per hour, and the volume of distribution initial estimate is 100 liters per kilogram. For the first order model, we will start with a absorption rate constant of 1, which is the default initial estimate. And we will see in the Phoenix model object there's actually an overlay of observed concentrations with what would the predicted concentrations be given fixed parameter estimates. And we can actually adjust that. There's a nice graphical overlay to investigate further. For the T-lag, we are using an initial estimate of 0.5 hours, which corresponds to the time of the first observed concentration in the profile. For the zero order model, the T-abs initial estimate is 4 hours, and this is determined from the plot. This corresponds to the T-max for the profile. Okay. At this point, I would like to switch to the demo portion. Okay. So I will pause here briefly and verify that everyone can see. Okay. But this, Bernd, can you see okay?
Yes, it's nice and clear. Thanks.
Thank you. Okay, so I have a Phoenix project here, and we have a single profile where we have times, measured concentrations, and in this example, we actually have the dose amount in the input data set. So this is 20 milligrams, which corresponds to 20 micrograms, where the units for the dose are matching the mass portion of the concentration units. And here we have the exploratory plot on a semi-log scale. You see that the first observation occurs at hour 0.5. So that's our estimate of the lag time. Sometimes it helps to fit absorption phases if one incorporates a lag time parameter. So that will be our initial estimate, 0.5. For the zero order model, we will use an estimate of 4 for the duration of the zero order input, since this corresponds to the maximum concentration, Tmax. At this point, we also have a first compartment elimination, as shown with this single slope on the log linear plot. So to go into the modeling, we will first determine some volume and clearance initial estimates, and this can be done by non-compartmental analysis. So we'll take the observation sheet and then send it to NCA and Toolbox, and then NCA. Okay, so go ahead under Setup Main, map the time and the CP to concentration. So the dosing, I can actually use the sheet, since the dose is part of the observation sheet, where the dose amount is mapped here, and the time of the dose is also listed here. For the calculation method, I'll choose linear up log down. That's for the AUC calculations, and then go ahead and run the non-compartmental analysis. Okay. So the parameters of interest from the NCA are going to be the volume and the clearance. So that's these two parameters. So the clearance estimate is about 45, maybe 46. The volume of distribution, 100 from NCA. We'll go back to the observation sheet, and at this point, work on a first-order absorption model. So in taking the observations, we'll send this to, this time select Phoenix modeling, and then Phoenix model. And I'll go ahead and name this first-order KA T-lag. Okay. At this point, I'll go to the Structure tab to set up the structural model. We only have one profile here, so there's no reason to do a population mode in this case. The type is PK. We will use clearance parameterization with an extravascular input and incorporate a T-lag and a one-compartment elimination. Then, as discussed previously, our convention is to use the differential equation models, and these are set by unchecking the closed form checkbox. Okay. So that's it for the built-in selections for the structural model. At this point, I'll come up to the mapping panel. Time is mapped automatically. The plasma concentration we will map as C-obs. And then the dose amount from the input spreadsheet will be mapped as the amount. So capital A means amount, and then the little a means absorption compartment. Okay. And at this point, I'm ready to go over to enter initial estimates. And this can be accomplished on the Initial Estimates tab. Okay, so the Initial Estimates tab shows initial concentrations, and then the smooth line are the fitted parameters. So this default that we're seeing is the profile that would result with a 20,000 microgram dose if all of these parameters took a value of 1. So we're actually going to adjust these. From NCA, the volume of distribution was approximately 100. The clearance, 45, and we can see that the predicted concentrations are beginning to overlay more with the observed. For the T-lag, our first observation occurred at 0.5 hours, so that will be our initial estimate for T-lag. And then for the absorption, the KA, we can actually lower this a bit and see if we're able to overlay better with the curve. But even from the initial estimate stage, we can begin to see that there are some problems. We can change to the log display and see the impact of changing these initial estimates. I could try maybe 0.5 for KA. Okay. These checkboxes on the left, these are to ensure if the checkbox is checked, the parameter will take a positive value. And at this point, I'll go ahead and copy these to initial estimates. And we're now ready to run the model. Okay. So with the initial fit, I'll start by looking at the predicted versus the independent variable here. So in this output plot, the red circles are the observations, and then the green line is the predicted. So as expected, we did have some trouble with the fitting, with the absorption phase. We also in the let's look at the final parameters, which are in the theta worksheet. So these are the final estimates for Ka, volume clearance, and T-lag. The standard errors are relatively high, as well as the coefficient of variation for several of the parameters. So since we had a bit of difficulty with a first-order model, our next step is to try a zero-order model. We'll go ahead and set that up. Go ahead and send the observation sheet to Phoenix Modeling and then Phoenix Model. And I'll start with a graphical zero-order model. And here we'll set up the structural model, again using differential equations. And this is going to be actually for the zero order, we're going to direct the input to the central compartment. Okay, so I'll leave that set to intravenous. We have a one-compartment elimination. Under the setup panel, map the concentration column. And then the dose is going to be A1. This is the amount in the central compartment. Okay. And just to show that you can set up a zero-order input in the graphical mode, we'll go ahead and change this to edit as graphical. So from the graphical interface, we're on this Model tab under Setup, and we have a toolbar palette here. We don't need to add any additional parameters at this point. But if we want to set a zero-order input, I can select the central compartment, and then in the bottom options panel, enter the zero-order input as either a duration or a rate. In this case, we will choose duration. And our initial estimate for duration was 4. I should comment, if you're entering in through the graphical mode, the zero-order duration, it's basically set to 4. It's not going to change. So this is a fixed value. Okay. Then on the initial estimates tab, can enter in our initial estimates for volume and clearance. Okay. If desired, I can compare on a log overlay. Okay. And then pressing these left-facing arrows will copy them to the initial estimates. At this point, ready to run the graphical model. Okay, so I'll start with the overlay plot. Okay, so here we see the observed concentrations overlaid with the predicted values, which is the green line. And this zero-order input was better able to, at least visually, was better able to capture the absorption phase. Here we have the theta values, where we found some values for volume and clearance. And so this was with a fixed zero-order duration. We can also compare the residual plots. So one of the examples would be to look at the first order with Ka and T-lag. And if we look at the residuals, this is the weighted residuals versus time. And actually see a sort of a banana shape to the blue line here. So we did have some problem with residuals. And this can be an indication of model misspecification. For the graphical zero order, if we look at the same output, Here, the blue line fits much more closely to the 0 line, which is the overall trend. We do have a little bit of an issue with residuals becoming small late in the profile. If one wants to, instead of entering a fixed 0-order duration, instead estimate the duration as a parameter, one can then copy the graphical model. And I will switch to text mode to estimate the 0-order input as a parameter, TABS. Okay, so I've taken my graphical model, and at this point we'll switch to edit as textual. Okay. And here the model code has been converted to text. So much of the PML has already been written. We have differential equations for the PK. Note that with the dose point, this duration statement is what determines that there's going to be a 0-order input. So I'm going to instead call this TABS instead of a fixed value of 4. These additional entries, I-dose variable, infusion dose variable, and infusion rate, these get built by default. They're actually not necessary in the statement. They just get constructed automatically. I can actually remove these. If there's nothing being done with them, they don't really need to be used. But as we see here from the text at the bottom, it's telling me that TABS is undefined. So TABS actually needs to be defined here. So what we will do is define it as a structural parameter. We'll go ahead and copy one of the existing statements, and then we'll say that TABS equals TV TABS. And then we also need to put in a initial estimate for TABS. So that will be done in the fixed effect statement, and then we'll put in the initial value of 4 for TABS. And we determined this from the plot. This was the Tmax for the exploratory plot. Okay, so I've entered in initial estimates. One other comment that Dan Weiner wanted to discuss is the fact that when you're modeling in this PML text mode, the error term is actually a fitted parameter as well, this C epsilon. When we ran the first order model and our final estimate for CEPS, it's actually shown on the structure tab here. And so it was 9.67823. I'm actually going to go ahead and rerun the first order model with this error term, and then run with the same error model in the textual 0-order model. Okay. So here we have the similar thetas as from the first run. We still have a high coefficient of variation for Ka, V, and T-lag. But I'm going to use, and when I reran the model, the error term didn't change much, nor did the final parameters. I'm going to actually put that in for the C epsilon estimate for the textual. And at this point, go ahead and run the 0-order textual model. Okay. So looking at the text model, here we have the final parameter estimates for volume, clearance, and TABS. So not too far from the initial estimates on volume and clearance. The 0-order duration final estimate was 4.5, but our parameter precision has gotten better. Here's the fitted plot from the results. And we can also look at the residuals. Again, we see that the overall blue line is very close to the 0 line. Our trend lines do show that the magnitude of the residuals gets smaller towards the end of the profile. However, all of the residuals are captured within 2 standard deviations. At this point, I'd like to stop sharing the Phoenix application and go back to the slides. So are the slides visible at this point?
Yes.
Great, thank you, Bernd. Okay, so a summary of the results. This is the built-in model with first order absorption and T-lag. We did have some difficulty fitting, and this was shown in the magnitude of our residuals as well as the parameter precision not being optimal. With the zero order duration with parameter T-abs, we were able to get a better fit graphically with the predicted overlaid with observed, and our parameter precision also increased. So in a summary here is we basically reviewed all of the different results comparing the zero order and the first order. And we have some remaining time, so I'd like to take a few moments for questions related to the fitting before moving on to the next segment, which is multiple dose simulation.
Okay, Chris. Yeah, there are a few questions that you can handle right now. There was one thing about you switched from extravascular to intravenous route of administration when going from the first order to zero order input model. Can you comment on this, please? Yeah,
sure, absolutely. So the question at hand, in the first order model, we described, apologies, I need to reshare.
Okay.
Yeah. So in the first order model, I have this selected, and we've set this to an extravascular administration. So this built-in model, what this will do is it will automatically incorporate a first order input, which is this Ka parameter, and also as well describe an absorption compartment. And for the zero order duration, we actually don't have an absorption compartment because it doesn't assume a proportional absorption is happening. It's just a constant rate of input. At the end of the day, the input does go to the central compartment. Whether it passes through an absorption compartment first, as is the case with the extravascular model, parameterized by Ka, or if it goes into the central compartment by a zero order input. And this is better represented by going directly into the central compartment and then defining that input. Instead of going through an absorption compartment, it is going through just a zero order duration. So it's a constant rate of input for 4 hours. So it's just a different way of describing the model. But at the end of the day, both models, the input does go ultimately to the central compartment.
Okay, yeah, just as we are on this model, on the built-in options, you've chosen a constant value here for zero order duration, and when you then you change to the textual model. But can you not also use the zero order duration tab, the graphical tab, to introduce a T-abs parameter?
Yeah, you could do that. So if you wanted to do that, what you would do is you would insert a parameter and give this parameter the name T-abs. And then in the zero order duration, instead of entering this, just enter as T-abs. And in this case, it will be estimated as a parameter.
Great.
And then at that point, you would go to the initial estimates tab, and you would need to supply the initial estimate for T-abs, which in this case is 4. And yeah, so yes, that's correct. This can be done in the graphical mode.
Mm. And for the zero-order input, is it possible to select infusion possible option and then use A1 rate equals dose divided by TAPS?
Yes, absolutely. So if we were modeling this as an infusion, we would, in the model, go back to the structural and then just check infusions possible. And then we would set this to a rate and call this A1 dose divided by TABS. So yeah, this would be the first order infusion input.
Mm-hmm. Okay, then you've shown in your textual model there was a fanning in the residuals. Can you use a different residual error model, like a multiplicative, to fix that? Or?
Yeah, we could certainly try that. So this is this would be the multiplicative error. So we have the in the multiplicative option, what you can do is use the multiplicative checkbox, and then update the error term. So you just basically need to write it in the PML code, and that is this error term here. So here we have the concentration plus the concentration times the epsilon. And in this case, I will go ahead and rerun in the textual mode. And we'll see the impact on the residuals. Okay. Okay, so we have shrunk down a bit. The trend lines now get closer in the middle. And as an aside, Dan Weiner sometimes comments on this and mentions that when you get this sometimes when there are few observations, as is the case with one profile.
Okay, well that looks good, Chris. Maybe just one final question before we move on with the next part of the session, and this actually leads to this next part of the session. Can this model also be used to estimate parameters from multiple dose data?
Yeah. So this is the multiple dose. I'm going to go ahead and switch back to my my previous run here. And then we will set up a multiple dose simulation. Okay, so at this point, I will go ahead and switch back to the slides. Okay. So I want to talk a bit about how to set up simulations in the Phoenix model object. So what we do is in the Run Options tab, so that's shown here at the bottom, we switch from simple run mode to simulation, and then set the number of points as well as the output range. So if I wanted to do a 72-hour simulation, I could, for example, probably want a rich number of points, so this is 10 points per hour. And then declare the Y variable, which is C, stands for predicted concentration. Okay. When it comes to simulating multiple doses, there are two different modes one can do it. If you have a regular dosing where the dose interval and the amount is always the same, for example, QD dosing of the same amount each day, you can use a feature called ADDL, which stands for additional doses. And this is actually entered on the Input Options tab. So we can select Input Options, check ADDL, and then set up the dosing schedule. So in this case, we have the delta time, the time between doses, which is a number of hours, in this case 8 hours. The dose point, A1, that's where is the dose being administered. In this case, it's the central compartment as a bolus. And then the dose amount, of course, which is 20,000 micrograms. Okay, and then under the setup dosing, we'll enter the initial dose amount, which is here, the time of the initial dose. And then the ADDL field is the number of additional doses you want to simulate. Okay. If you want to do a variable or uneven dosing schedule, instead of using ADDL, you can just go to Setup Dosing, check Internal Worksheet, and then fill out a dosing schedule. In this case, I did the amounts were the same, but the times are not QD or TID. It's 0 and 8 hours on the first day, and then 24 and 32 on the second day, 48 and 56 on the third day. Okay, so that's just an example, but you could vary the amounts here as well by changing the amount in the A1 column. Okay, so I'll go back to the Phoenix application. Okay, and if I want to set up a simulation for my textual zero order, I'll go ahead and copy the text model. And I'm going to call this sim zero order with the ADDL option. Okay, so in this case, we'll do a multiple dose simulation. And then how do we determine the dosing schedule? Well, one aspect of this is the half-life. This is from NCA, so I'm bumping back to NCA. We actually see that this is this compound has a short half-life, only 1.6 hours. So we probably want to set up a dosing schedule where the repeated dose occurs before all of the previous is eliminated. So this number times 5 is approximately 8 hours. So for that reason, 8 hours will be the interval between doses in the simulation. So setting up the simulation, the first thing is to go to the Run options. And we'll change the mode to simulation. If I want to simulate out to, say, 72 hours, add a rich number of points. And then my variable is capital C. And it's important that this is capitalized as C. In this case, we'll go ahead and move the dose. We're no longer reading it in from the sheet, but we're instead defining it on the input options. In the input options, check ADDL, and then press Add to enter a new dosing cycle. The delta time will be 8 hours. The dose point is the central compartment, and the amount is 20,000. Okay, and notice in the mapping panel this ADDL column appeared. You can read in the number of additional doses from a spreadsheet. Or the alternative is to go to Setup Dosing, check an internal worksheet, and then enter the dose amount, the time of initial dose, which is 0, and then specify that we have 6 additional doses. At this point, we'll go ahead and run a simulation. Okay, so there are two outputs of interest here. One of them is the spreadsheet, which shows the simulated concentrations. Notice that based on the number of points entered, it's basically once every 0.1 hours. And then you'll also get this output sheet called individual simulation. If desired, I can change the layout a bit to make it a bit wider. So it's a little bit easier to visualize the multiple dose simulation. Okay, so this is simulated with a total of 7 doses out to 72 hours. And then if one wants to do an uneven dosing schedule, this is also possible. In this case, I'll go ahead and copy my, my model fit again. And we'll call this sim zero order uneven dosing. Okay. So to set up a custom dosing schedule rather than a set cycle, I again will move the dose, no longer being read in from the sheet, and instead enter my schedule under Setup Dosing. We use an internal worksheet and enter in some dose times, time of dose events. So maybe in this case, the patient only received the dose at the beginning of the day, and then 8 hours later, and then there was no evening dose, for example. Okay, and so at this point, I'll go ahead and go to the run options, set it to simulation, and set the time range, and then the Y variable. And we'll go ahead and execute. And here we have the simulation with the uneven dosing schedule. Okay, so that concludes the demo portion for the simulation. Are there any additional questions at this point about simulation or multiple dosing? So please do continue to type your questions as you have them. We will also address questions on the forum.
Yeah, Christian, I was on mute, sorry. Yeah, there was one question about the A1 rate column. This is empty here. Maybe you can comment on this.
Yeah, sure. So I happened to bump back to the slide, but it's on the same slide. So this A1 rate, this is for infusion models. So if you had an infusion rate, then you would enter it there. If it's not an infusion, if it's a bolus, as was the case here, then we can just leave the A1 rate empty.
Okay, maybe time for a final question. If there were multiple profiles or patients, can you simulate each using their individual PK estimates?
Yeah. So if there were multiple subjects, what you would do is go to Setup and then Parameters, and then check Use an internal worksheet. So in this case, we have no sort variable. So what you would need to do is let me copy paste this. Okay, so I'm going to set up a new worksheet. Okay. And let's say this is for subject 1. And if we were to have a bigger spreadsheet here, okay, and then if I were to read this worksheet in, and then sort by subject, in this case, you could go to Setup Parameters, and now you get the opportunity here on a per subject basis. So maybe subject 1 had 100 for volume, 45 for clearance, 4 for T-abs. But the second subject maybe 150, 50, and their T-abs initial estimate was 5. So you would just use this worksheet under Setup Parameters. Okay. Then if you run the simulation, the simulation worksheet now has 2 different simulations, one for each subject, yeah, with the different values for the parameters.
Okay, very
Any
nice.
other questions?
Very nice. Yeah, but we have run out of time right now, so maybe you can handle those questions when we post them to our forum.
Okay. Great. So what we'll do is go back to the slides. I have a few more comments to make to wrap up the session. The first comment is I want to make you all aware of a website called Certara University. Through Certara University, there's a wide range of on-demand as well as classroom courses that you can sign up for. And so the classroom courses are set up with an instructor, a live instructor that presents, and then you attend and perform the exercises. Or you can also sign up for the on-demand feature, where you're basically doing a web-based learning. There's a tutorial video with some practice questions at the end of each, and it's up to you which mode you want to sign up for. But there's a wide range of courses, including introductory, intermediate, and advanced, instruction in Phoenix Wind on Lin, population modeling using NLME, as well as the IBIVC toolkit. There are also courses on fundamentals of pharmacokinetics and pharmacodynamics, non-compartmental data analysis, programming bootcamp for applications such as R, partner lectures and webinar series. So please visit our website. And again, this will be posted to the forum. So if you want to continue your learning, this is another venue that you can use. Okay, so the materials, we will post this to the forum. This is at support.certara.com/forums and then under PML School. So just click this URL. We will provide the model text as a file download as well as the Phoenix project that was used during the demo. As well, we will address questions and comments on the forum. And last but not least, I want to make sure to make you aware that the next event in our series will be in 2 weeks' time. On Thursday, February 16th, Dan Weiner will be presenting the topic of allometric scaling in PML modeling. Okay. So that concludes the session, and we hope to see you at the next event and in future webinars in the series. So thank you very much for your time and your questions today.